In this video, we're going to talk about power, which is an important concept when we talk about it in terms of physics, because it's one of these words that gets used a lot, but has a very specific meaning in physics. So power, this is the rate of change of work done. That means it's also effectively the rate of change of the energy of a system. More properly, it's kind of rigorously defined as the rate of change of the work done, but because work is equal to changes in energies, it's also the rate of change of, it's the rate of change of energy. So properties, power is the, power, the quantity is, it is also a scalar. It doesn't have a direction associated with it. It is just an amount. The variable that we use for power is capital P. The units are, as you might expect, 1 joule per second. Yeah, this isn't right. Leave it as change of energy. That's a clearer way of expressing it. There's layers to that we'll get to later, but you don't need to worry about it for now. It's 1 joule per second, which is also known as 1 watt, which we represent with a capital W, so that's watt. And you can write this in all sorts of other ways. If you're curious of all the other things, just go back in and replace a joule with anything that you know a joule is related to, and you can see all sorts of different things. And the equation for power is that power equals work, change in work over change in time, which is also, we can write as change in energy over change in time. And this can be high either because the work is large or the time is small, or vice versa. You can have a low power because the work is either very small or it's done over a long period of time. So as a first example, an athlete is training by doing pull-ups if they have a mass of 75 kilograms and they lift their body a total of 0.75 meters in 1 second. What is their power output? So power is equal to work over change in time. So we've got this work over time, and that's going to be equal to the force parallel times the change in distance. And the force, if we think about our free body diagram, how hard do they have to pull to move their body up? They have Fg pulling downwards, and then upwards, that's the force that they're pulling with. So this should be equal to the force pull, which is equal to mg times delta x over delta t. So we can plug things in. We'll get 75 kilograms times 9.8 meters per second squared times delta x of 0.75 meters divided by 1 second. And you can calculate this out. You're going to get some number, and it will be in watts, and we can check that because we'll see a kilogram, meters squared per second squared on top, which is the same as a joule. A joule per second is the number of watts. I'm not sure what this will give you, but eyeballing it, 75 times 0.75, that would be 3/4 of 75, which is going to be 60-ish, a little less than that, probably 50-something. So we're looking at roughly maybe 580-ish, 570, 560. Really eyeballing it roughly there, but 500 to 600-ish watts in this example. Example 2, a 750 kilogram engine starts from rest and has an average power output of 30,000 watts for a total of 3 seconds. What's its final speed? Well, we're going to look at the power equals work over delta T. Now, because we don't know the forces, we need to use the alternate form, which is the change in energy over change in time. And the change in energy is going to be because of the change in kinetic energy, because that's where all this, where we're assuming that all the energy from the engine is going to. So that's going to equal 1/2 m times the final velocity squared minus the initial velocity squared over delta T is equal to the power. So we can then rearrange that as power times delta T is equal to 1/2 m v squared minus v naught squared. V naught squared is 0 because it starts at rest. So we have 2 times the power output times the change in time divided by the m is equal to v squared. So square root of 2p delta T over m is equal to v, which I'm just going to write these out so we can see the units and double check them, but you'll plug this into your calculator to find the actual value. 2 times 30,000 watts times delta T, which is going to be 3 seconds, over kilograms of 750 kilograms, square rooted. So a watt is a joule per second. If I multiply that by seconds, the seconds cancel. And then I have joules per kilogram. And if you remember, a joule is 1 kilogram meters squared per second squared. So if I have 1 kilogram on the top and bottom, those cancel. And then remember, these units are square rooted. So I will get meters per second, because I'll square root this, get meters per second. So this will be some number, meters per second. 60,000 times 3, 180,000 divided by 750. It's getting tough to do that math, but 750 is roughly half of that plus some. Yeah, it's going to be rough to do that in my head, but you've got a calculator, you can check that. If you're not sure, you want to double check with me, let me know, and I'll help double check your math there.